Remember the first time you truly interacted with one of these AI models? That moment when it felt less like a sophisticated piece of software and more like, well, something else. Perhaps it was generating incredibly creative art, or maybe surprisingly coherent code, or simply answering a complex question with an uncanny fluency that left you thinking, okay, what just happened here? Well, today we're taking a deep dive into the technology that powers so many of those moments. Generative Pre-trained Transformers, or GPT, our mission. To really unpack its architectural brilliance, trace its astonishing evolution, understand the sophisticated process of its training, explore its sweeping impact across industries, and confront the significant challenges it presents, all while looking towards its mind-bending future and the ambitious quest for artificial general intelligence.
Yeah, and we've got a fantastic stack of sources for this deep dive. Everything from seminal papers like Attention is All You Need, that really laid the groundwork, to detailed overviews of OpenAI's trajectory and analyses of the broader competitive landscape. It's quite a rich tapestry of information. It's truly going to help us grasp the phenomenon of GPT, moving beyond the headlines to understand the fundamental mechanics and its profound implications.
Definitely. So if you've ever felt maybe a bit overwhelmed by the sheer volume of AI news or just wanted to understand the real brains behind the AI boom, then this deep dive is for you. We're going to give you the context, the surprising facts, and hopefully those aha moments you've been looking for, allowing you to cut through the noise and truly grasp this transformative technology. Okay, so let's start right at the very beginning with the name itself, Generative Pre-trained Transformer. It sounds like a mouthful of technical jargon, right? But each of those three words is actually a vital clue to understanding its profound capabilities. Let's kick off with generative. This is absolutely fundamental. Unlike older AI models that were primarily designed to classify or analyze, telling you if an email is spam, for instance, GPT's core purpose is to create new, coherent content. Think of it less like a database lookup and more like a master improviser. When you give it a prompt, it doesn't just retrieve a pre-written answer. No. Instead, it uses what's called an autoregressive process.
Now, that simply means it predicts the most statistically probable next word or token in a sequence, building on all the words that came before it. So if you ask it to write, say, a Shakespearean sonnet, it's not searching for sonnets Shakespeare already wrote. It's reconstructing new phrases and sentences in that specific literary style, building it word by word, line by line, based on the patterns it learned from, well, vast amounts of text. Okay, then we have pre-trained. This refers to its initial foundational training phase. And when we say massive scale, we truly mean it, like mind-boggling scale. GPT models are pre-trained on an enormous, incredibly diverse, and critically unlabeled text corpus. Imagine the sheer volume. Millions of books, articles, web pages scraped from the internet, just vast. This unsupervised stage is where the model learns statistical patterns, grammar rules, syntax, semantic relationships, and an astonishing amount of general world knowledge. To give you an analogy, think of it like a baby learning language. A child doesn't start by being explicitly taught grammar rules or definitions, right? Instead, they listen. They listen to everyone around them for years, absorbing patterns, context, and meaning, long before they're ever asked to construct a specific sentence or answer a particular question. That's precisely what this pre-training phase does for GPT. It creates a foundational understanding of language without being told what specific tasks it will eventually perform. And finally, transformer. This is the foundational neural network architecture itself. It was a revolutionary design, introduced by researchers at Google in a landmark 2017 paper titled Attention is All You Need. We'll definitely get more into that later. Its core innovation is something called self-attention, which allows the model to process all parts of an input sequence in parallel. This is incredibly important because it means it can capture complex, long-range dependencies. You know how words at the beginning of a long sentence relate to words way at the end, for example. It handles that far more effectively than its predecessors. This transformer architecture is the technical backbone that makes all the generative magic and the unprecedented scale of these models even possible.
That's a crucial breakdown, yeah. Because Generative Pre-trained Transformer isn't just a technical name. It really outlines a fundamental shift in how we approach AI. Before this, the landscape was, well, dominated by highly specialized, task-specific models. If you wanted to do sentiment analysis, you built a model just for that. For question answering, another entirely separate model. And this required expensive, manually labeled data for each individual task, super inefficient. The combination of a generative objective, unsupervised pre-training on web-scale data, and the powerful, parallelizable transformer architecture. It fundamentally freed us from that cycle. It created these general-purpose foundation models that with minimal additional training could adapt to a multitude of applications. This wasn't just an improvement, it was a true paradigm shift for the entire field. A really big deal.
And the organization behind this paradigm shift is just as interesting as the technology itself, wouldn't you say? Let's talk about OpenAI for a moment. OpenAI was first announced back in 2015, and it had this remarkably ambitious and, well, noble mission. It started as a nonprofit AI research company, backed by prominent figures like Sam Altman and Elon Musk, who collectively pledged $1 billion. Quite a start. Their founding vision was crystal clear: to ensure that artificial general intelligence, AGI, AI systems that are generally smarter than humans benefits all of humanity. End quote. The initial idea was to focus on long-term fundamental AGI research, free from commercial pressures, to prevent, a single company or nation from dominating this potentially world-changing technology. However, this grand vision soon ran into a very practical problem: money, lots of it. The sheer computational cost of training increasingly larger language models like GPT-3, for instance. We're talking tens of millions of dollars just for the raw compute resources. That kind of cost meant that a traditional nonprofit just couldn't keep pace. It wasn't sustainable. So, to attract the necessary capital, OpenAI underwent this pivotal restructuring in 2019. They transitioned to what they called a capped profit model. This meant creating a for-profit subsidiary that was still controlled by the original nonprofit, kind of a hybrid structure. This allowed them to raise substantial investment, most notably from Microsoft, while still capping investor returns and ensuring any excess value was channeled back to the nonprofit mission. This, in essence, was the financial fuel that powered the exponential scaling of the GPT series we see today. And while Sam Altman has definitely become the public face of OpenAI, it's important to acknowledge the truly collaborative effort behind those first GPT models. The original 2018 paper, Improving Language Understanding by Generative Pre-training, listed Alec Radford, Karthik Narasimhan, Tim Salomons, and Ilya Sutskever as authors. Radford is often credited as a primary driving force behind the initial GPT-1 project.
And of course, the incredible success of these foundational models ultimately set the stage for the public launch of ChatGPT in November 2022, which, let's be honest, truly brought generative AI into the global mainstream and ignited the current AI boom we're all experiencing. Now, to fully appreciate just how revolutionary GPT was, it really helps to understand what the world of natural language processing, or NLP, looked like before 2018. What was the state of play? What was the challenge it was designed to solve?
Exactly. That context is key. Before the Transformer, the state-of-the-art models for sequence-based tasks were primarily recurrent neural networks, or RNNs, and their more advanced cousins, long short-term memory networks, LSTMs. These models processed text sequentially, word by word by word, like trying to read a very long, complex sentence, and by the time you get to the end, you've kind of forgotten the nuance of the beginning. That was the core challenge for RNNs. It's called the long-range dependency problem. The influence of earlier words would diminish or vanish, making it incredibly difficult to connect distant concepts within a text. And this sequential processing also created a major computational bottleneck. It made training on large texts agonizingly slow and prevented the kind of parallel processing that modern hardware like GPUs offers. Furthermore, the prevailing methodology relied heavily on supervised learning. For every single NLP task, whether it was sentiment analysis, question answering, or language translation, you largely needed to create a bespoke model architecture and then train it on a massive manually labeled dataset specific to that task. This was prohibitively expensive and incredibly time-consuming. Really, like building a custom bridge for every single river, as you said earlier. Now, the concept of pre-training did exist in earlier, more rudimentary forms, like word-to-vec. But that offered static word embeddings, meaning the word bank, had the same numerical representation regardless of whether it was a river bank or financial bank. Not ideal. Later, models like Elmo introduced contextual embeddings, which was definitely an improvement. But they still required significant task-specific architectural modifications for fine-tuning. Still clunky. What GPT-1 really achieved was this powerful synthesis of ideas. It took a semi-supervised pre-training and fine-tuning approach and applied it to the powerful, non-sequential transformer architecture in a largely task-agnostic way. This effectively solved the parallelization and long-range dependency problems of RNNs while simultaneously overcoming the data and customization bottlenecks of the previous supervised learning paradigm. It truly set a new course for the entire field of artificial intelligence. It was foundational.
Okay, that brings us perfectly to the very heart of GPT's power: the transformer architecture itself. And to understand that, we have to go back to that single foundational paper that truly shifted the paradigm. Right, so in 2017, this team of 8 researchers at Google published a paper that just made waves across the entire AI community. It was simply titled, "Attention is All You Need," which is a pretty bold title, actually. And this wasn't just another research paper. It was, well, a bombshell. Its central and most revolutionary claim was that a neural network architecture based solely on attention mechanisms could not only match, but significantly outperform the dominant models of the time, which relied on complex recurrent or convolutional networks. This is a radical departure. They were effectively saying, hey, we don't need all those complicated sequential layers anymore. Attention is enough.
That's right, a huge claim. And the transformer completely dispensed with those recurrent layers. And that wasn't just a minor tweak. It gave them 2 massive advantages. First, the models achieved superior results on tasks like machine translation. They improved the state-of-the-art BLE score on English to German translation by over 2 points, which is a significant jump in that field. Real performance boost. But second, and perhaps even more consequentially, by removing the sequential nature of RNNs, the transformer architecture became incredibly parallelizable. What that's meant in practice was that it could take full advantage of modern graphics processing units, or GPUs. It could process all parts of an input sequence at once, simultaneously. This dramatically reduced training time, cut it down hugely. This newfound efficiency and scalability is the direct technical enabler that made the massive scale of models like GPT-3 and GPT-4 even possible. Honestly, without this paper, the AI world as we know it might simply not exist today. It unlocked a whole new dimension of possibilities.
Okay, so if the transformer relies completely on attention, how does this self-attention mechanism actually work? What is it doing under the hood? It sounds almost, intuitive, but how does it technically function?
Well, a critical insight here is how self-attention overcomes the limitations of previous models. It's sort of like having every word in a sentence simultaneously whisper its relevance to every other word, and then dynamically highlighting the most important connections. Fundamentally, self-attention allows the model, when processing a single word, to dynamically weigh the importance of all other words in the same sequence. It's how it builds a contextually rich representation for each word by looking at the entire input at once. For instance, think about the sentence, "The judge issued a sentence." Self-attention can learn that the word sentence is strongly related to judge and issued, thus correctly interpreting it as a legal penalty rather than, say, a grammatical structure. This ability to model dependencies without regard to their distance in the input or output sequences is a key advantage over older sequential architectures that really struggled with that long-range context. Now, the underlying math for this uses what's known as the query, key, value, or QKV model. Sounds complex, but the idea is fairly straightforward. For each input token, after it's converted into a numerical vector, the model essentially generates 3 different perspectives. A query, which is like asking what information is relevant to me. A key, which acts as a sort of label for each token that other queries can match against. And a value, which contains the actual information, the substance, to be passed on. The self-attention process then calculates how well each word's query matches every other word's key. This gives a score of relevance. These scores are then normalized and used to create weights, showing how much attention the current word should pay to every other word. Finally, these attention weights are multiplied by the value vectors and summed up, creating a new, contextually enriched vector for the original word. It's a sophisticated process, yeah, but it ensures the model focuses its computational attention precisely where it's most needed.
Right. And to capture even more nuanced relationships simultaneously, whether they're syntactic, semantic, or linking pronouns to their antecedents, the transformer doesn't just use one attention mechanism. It employs what's called multi-head attention, right? Can you unpack that a bit?
Exactly, good point. Instead of just one set of query, key, and value mechanisms, the model has multiple parallel attention heads. Each head has its own unique learned matrices, its own set of Q, K, and V transformations. Think of each head as looking for a different kind of relationship in the text. One head might focus on grammatical dependencies, like subject-verb agreement. Another might focus on semantic similarity words that mean similar things. And maybe a third looks at co-reference, like linking he or she back to a specific person mentioned earlier in the text. Each head independently performs the self-attention calculation, allowing the model to focus on different aspects of the input sequence at the same time. In parallel, the outputs from all these heads are then combined, usually concatenated and linearly transformed to produce a truly comprehensive, context-rich representation for each token. More dimensions of understanding.
Okay, that makes sense. Now, there's a subtle but absolutely crucial piece to this puzzle. Self-attention, by its nature, treats input words almost like an unordered set, right? Like a bag of words. If you shuffled the words in a sentence, the self-attention mechanism might produce a similar output technically, but the meaning of the sentence would be completely lost. So how does the transformer understand word order? That seems vital.
Ah, yes. That's where positional encoding comes in. And it's a really clever solution because you're right. Without it, the model would be permutation invariant, which is bad for language. So before the word embeddings are fed into the very first transformer layer, a unique positional vector, almost like a timestamp or an address for each word, is added to each word's embedding vector. This vector contains specific information about the word's exact position in the sequence, word 1, word 2, etc., and potentially its relative position. While the original attention is all you need, Paper used mathematical sine and cosine functions for this, which have nice theoretical properties. Later models, including the GPT series, often use learned positional encodings. In this case, these positional vectors are just parameters that are trained along with the rest of the model weights. It's a subtle detail, but it's absolutely crucial. It's what lets the AI understand who did what to whom in a sentence and correctly interpret the sequence, the grammar, the flow.
Got it. And finally, let's look at the specific architecture of the GPT models themselves. The original Transformer paper described an encoder-decoder model, which makes sense for tasks like machine translation, where you have an input sentence in one language, processed by the encoder, and you need to generate an output sentence in another by the decoder. But GPT models take a slightly different approach, don't they?
That's an important distinction, yes. GPT models are architected as decoder-only transformers. They effectively discard the entire encoder stack and use only the decoder stack. This specific design is exceptionally well-suited for generative language modeling, where the primary task is to predict the next token in a sequence given all the preceding tokens. That's the core GPT task. Now, to ensure this autoregressive property during training, meaning it only predicts based on what it's already seen or generated, a crucial technique called masking is applied within the self-attention mechanism in the decoder. A look-ahead mask is essentially placed on the attention scores. This mask prevents the model from attending to or seeing any subsequent tokens in the sequence when it's trying to predict the current token. This forces the model to make predictions based only on the known past. This masking step, it sounds simple, but it's deceptively simple and absolutely fundamental. It's what allows GPT models to learn to generate text in a truly autoregressive way, one token at a time, building coherent narratives from scratch. It's the basis of all its generative capabilities.
Okay, now that we've got a handle on the architectural blueprint of the Transformer, let's trace the truly breathtaking evolution of the GPT series itself. It's really a story of exponential growth, isn't it? Where each successive model wasn't just an incremental improvement, but often a qualitative leap in capabilities, continually pushing the boundaries of what AI could actually do. Our journey begins with GPT-1 back in June 2018. OpenAI introduced this model really as a proof of concept, demonstrating the viability of that generative pre-training approach we just talked about. By today's standards, it was relatively modest. It featured a 12-layer, 12-head, decoder-only transformer architecture, and it had 117 million parameters. Seems small now, but it was significant then. It was pre-trained on the book corpus dataset, which contained over 7,000 unpublished books. These were specifically chosen for their long, contiguous stretches of text, which is ideal for learning narrative coherence and long-range dependencies. The core innovation of GPT-1 was demonstrating that systematic two-stage training process. Unsupervised pre-training for general language representation, followed by supervised fine-tuning for specific NLP tasks with minimal architectural changes needed.
And its impact was significant, yeah. It truly validated the generative pre-training approach. It improved upon the state-of-the-art on 9 out of 12 tasks in the GLUE benchmark, which is a standard set of NLP tasks. So it essentially proved that a single general-purpose language model could achieve broad competency across various different tasks. It was the first solid step on this remarkable journey we're still on.
Then came GPT-2 in February 2019, and this was where things really started to get, well, interesting, and maybe a bit controversial. It scaled up in pretty much every dimension. The largest version boasted 1.5 billion parameters. That's a 10-fold increase from GPT-1. Huge leap. It also featured 48 layers and an expanded context window of 103024 tokens. And GPT-2 was trained on a much larger and more diverse data set called web text. This was a 40 gigabit corpus of text scraped from about 8 million high-quality Reddit links.
And the key discovery here was zero-shot learning. The model demonstrated that at this larger scale, it could perform a wide range of tasks without any explicit fine-tuning at all, just by being given a natural language prompt. You could prompt it with, say, translate to French, I love you, and it would produce je t'aime, just like that.
And the quality of its generated text was so surprisingly human-like. that OpenAI initially took the controversial step of releasing only smaller versions of the model. They cited concerns about its potential for malicious use, like generating believable fake news articles or automated spam.
It really put a spotlight on the ethical tightrope walk, didn't it? I remember thinking, wow, have we just unleashed a super-powered spam bot or fake news generator? It certainly made for some interesting headlines and forced everyone, researchers and the public alike, to start considering the broader societal implications of these powerful new tools much more seriously.
The scale just kept climbing. GPT-3 arrived in June 2020. This model was another order of magnitude larger. We're talking 175 billion parameters, just enormous. It had 96 layers and a 2048 token context window, double that of GPT-2. Its training data was massively expanded too, to over 570 gigabytes. This included filtered versions of Common Crawl, web text, digitized books, and Wikipedia. Just a huge slice of the internet and literature.
Yeah, and what GPT-3 really brought to the forefront was in-context learning, sometimes called few-shot learning. This was a genuine game changer. It hinted that at a certain scale, these models aren't just memorizing patterns. They're actually learning to recognize and apply abstract task formats on the fly, just from the prompt itself. You could give it, say, 2 or 3 examples of sentiment analysis directly within the prompt, then provide a new sentence, and it would correctly classify its sentiment without ever changing the model's underlying weights. No fine-tuning needed for that specific task. This model could write surprisingly good poetry, generate functional code snippets, answer trivia questions, and even perform simple arithmetic, all just from natural language prompts. And its release via an API really democratized access to a frontier large language model for the first time, sparking this incredible wave of innovation and new applications from developers everywhere.
But raw power, as we quickly learned with GPT-3, isn't everything, is it? Its outputs, while often brilliant, could also be biased, toxic, factually incorrect, or just completely fabricated those hallucinations we talked about. So the next big leap wasn't just about scaling up further. It was about a concept called alignment, basically teaching the AI to be helpful, harmless, and honest, aligning it with human values. So in early 2022, OpenAI introduced InstructGPT. This is a series of models specifically fine-tuned to better follow user instructions. And this was achieved through a novel technique called reinforcement learning from human feedback, RLHF, which we'll definitely dive into in more detail later. It's super important. This process essentially trained the model to produce outputs that human labelers consistently preferred, making it more helpful and safer. And then in November 2022, well, the world changed with the launch of ChatGPT. This was a conversational variant based on the GPT 3.5 series, which incorporated InstructGPT methods, and crucially, it was released free to the public.
And its intuitive nature, its ease of use, and its remarkable conversational ability led to just unprecedented viral adoption. Reaching 100 million users in just 2 months, that's faster than TikTok or Instagram. It single-handedly launched the global AI boom we're currently in. It really showed us what was usable by everyday people, and that's when things really took off for the public consciousness.
Okay, moving on to GPT-4, released in March 2023. This marked another significant leap, focusing on advanced reasoning capabilities and expanding beyond just text-only inputs. OpenAI became noticeably more secretive about its technical details, citing competitive and safety concerns. But it's widely believed to use a mixture of experts, MEI architecture, with approximately 1.7 trillion parameters, though that's not officially confirmed.
Right, a lot of speculation around the exact size and architecture there. But its key advancements were clear. First, multimodality. It became the first flagship model in the GPT series to accept both text and image inputs. This allowed it to perform tasks like describing a picture in intricate detail, explaining a complex diagram, or even generating the code for a website from just a hand-drawn sketch. Pretty amazing stuff. It also demonstrated vastly superior reasoning abilities. Famously, it passed a simulated bar exam in the top 10% of test takers, whereas GPT 3.5 was way down in the bottom 10%. A massive improvement in complex reasoning.
And it was significantly more creative, more reliable, and better at following nuanced and complex instructions. OpenAI put a great deal of effort into reducing hallucinations and improving safety guardrails compared to GPT 3.5. It also expanded its context window significantly. Initially up to 32,000 tokens, and then GPT-4 Turbo, released in November 2023, pushed that even further to 128,000 tokens, which is equivalent to processing something like a 300-page book in a single prompt. Huge capacity.
And this truly brings us to the latest iteration, pushing towards native omnimodality. This isn't just an incremental upgrade. It feels like a foundational shift towards truly human-like interaction. It's perceiving the world in a much richer way now, bridging the gap between our human senses and the AI's understanding.
Exactly. And most recently, in May 2024, we saw the release of GPT-4o, where the O stands for Omni. This signaled a clear strategic shift towards creating a single, seamlessly integrated multimodal experience. Unlike previous voice modes that relied on a clunky, slow pipeline of 3 separate models, one for speech-to-text, then GPT-4 for processing, then a third for text-to-speech GPT-4o is different. It's a single end-to-end model trained across text, vision, and audio natively.
And this unified architecture has profound implications. It's not just neater engineering. It dramatically reduces latency. The average audio response time is just 320 milliseconds. That's comparable to human conversational speed. This enables really fluid, real-time interactions like simultaneous translation during a conversation. And because it processes audio natively, it can perceive and respond to nonverbal cues like tone of voice, background noises, or even multiple speakers interrupting each other. It can also generate outputs with a range of emotions and tones, much more natural.
Plus, its vision capabilities are fully integrated into the conversational flow. You can literally have a spoken conversation with the AI about what your phone's camera is seeing in real time. Performance-wise, it matches the intelligence level of GPT-4 Turbo, but it's significantly faster and, crucially, 50% cheaper to use via the API. This makes that frontier-level AI intelligence more accessible than ever before. Just consider how this opens up possibilities for interactions that feel truly natural, almost like speaking to another person. And OpenAI's roadmap continues to evolve beyond this. They've announced smaller, highly efficient models like GPT-4o Mini for July 2024, and have signaled plans for GPT 4.1, GPT 4.5, and eventually the unified GPT-5 system. The pace is just relentless. So, okay, how do these incredible models actually get made? How are they trained? The remarkable capabilities of modern GPT models aren't just a function of their architecture, that transformed design we discussed. They're also the product of a really sophisticated multi-stage training process. You can almost think of it like a funnel. It starts with this vast, unfiltered ocean of data and progressively refines the model's behavior using smaller, higher quality, human-curated data to ensure it's aligned with our intentions and values. The first stage, and the most computationally intensive by far, is unsupervised pre-training on web-scale data. The main objective here is just to build a comprehensive model of language and the world it describes. Simple goal, massive task. The model learns grammar, syntax, factual knowledge, reasoning patterns, all the subtle nuances of human communication, simply by being exposed to an immense volume of text data. A large decoder-only transformer model is initialized with random weights, just random numbers basically. Then it's trained on massive and diverse unlabeled text data, things like Common Crawl, which is a huge web scrape, digitized books, Wikipedia articles, etc. The training task itself is deceptively simple, next token prediction. The model is given a sequence of text, and its only job is to predict the most probable next word or subword, token. It does this over and over and over again for literally trillions of tokens, each time adjusting its internal parameters, its weights, to minimize the difference between its predictions and the actual next token in the training data. Learning by predicting.
And this phase, this pre-training, is what necessitates those massive data centers and thousands upon thousands of GPUs running for months. The sheer scale of GPT-3's training, for instance, was just mind-boggling. It demanded computational power equivalent to millions of hours on thousands of top-tier GPUs, a truly colossal undertaking that pushed the boundaries of what was technologically feasible at the time. And this is also the stage with the highest environmental impact, due to that massive energy and water consumption we'll touch on later. Now, the outcome of this stage is what's called the base model. This model is incredibly knowledgeable, fluent, can generate very human-like text, but it's not yet a helpful assistant, not by a long shot. Its objective is purely to complete a given text sequence in the most statistically likely way based on its training data. It's a completion engine. So imagine that child again, the one who has read every book and listened to every conversation on the internet. They're incredibly knowledgeable, sure, but they don't necessarily know how to behave appropriately or answer a specific question helpfully or truthfully. That's our base model. It's prone to generating outputs that are factually incorrect, biased, toxic, or simply unhelpful because it just reflects the raw, unfiltered nature of its web-scale training data.
Right. So once this incredibly knowledgeable but sort of raw and unrefined base model has absorbed all that internet data, the next critical step is to actually teach it how to be useful, how to follow instructions properly, how to be a good assistant. And that's where stage 2, supervised fine-tuning, or SFT, comes into play. This stage aims to steer the base model away from being just a simple text completer and towards being a useful instruction-following or conversational agent. Here, OpenAI curates a much smaller, but very high-quality dataset of desired model behavior. This dataset consists of prompt-response pairs, which are actually written by human labelers, real people. These labelers are given prompts like user questions and asked to write out ideal, high-quality responses that exemplify the kind of helpful, detailed, honest, and safe output the final model should produce. The pre-trained base model is then trained or fine-tuned on this supervised dataset, adjusting its weights again, but this time to make it more likely to produce responses in the style and format demonstrated by these human labelers. Learning by imitation.
Exactly. And this data for SFT is significantly more expensive to create than the unlabeled data used for pre-training because it requires the time and expertise of skilled human writers to generate those high-quality examples. It's a bottleneck. The outcome is the SFT model. This model is much better at following instructions and engaging in dialogue than the raw base model. It has learned the format of being an assistant, how to structure answers helpfully, but it can still struggle with nuance. It might still be led to generate undesirable content if prompted in certain ways. And this step really raises that important question again. Who are these human labelers? What are their backgrounds? Whose values and perspectives are they implicitly or explicitly instilling into the AI's core behavior? The choices made here in creating this SFT dataset profoundly shape the AI's emerging personality and its ethical boundaries. It's a critical point of influence.
That's a crucial point, absolutely. And that leads us directly to stage 3. Reinforcement learning from human feedback, or RLHF. This is the final and arguably the most nuanced stage of the training process, and it was a key innovation for making models like InstructGPT and ChatGPT so much more aligned and useful than raw GPT-3. It's crucial for aligning the model's behavior with complex and often difficult to specify human values like helpfulness, harmlessness, and honesty, things that are hard to define in a simple data set. This RLHF process involves 2 main steps. It's quite clever. First, training a reward model. The SFT model, the one we just discussed, is used to generate several different responses to various prompts, maybe 4 or 5 variations. Then, human labelers are presented with these different responses and asked simply to rank them from best to worst. They rank them based on criteria like helpfulness, truthfulness, safety, adherence to instructions, etc. This ranking data, which captures subtle human judgments and preferences, is then used to train a separate model called a reward model. This reward model's job is essentially to act as a proxy for human judgment. It learns to take any given prompt and response pair and output a scalar score or reward that predicts how a human would likely rate that response. It learns human preferences.
Okay, so you have this AI judge that mimics human preferences. What's the next step?
The second step is fine-tuning the language model with a reinforcement learning algorithm, often using something like proximal policy optimization, or PPO. In this phase, the SFT model acts as an agent in an RL environment. It generates a response to a random prompt from a dataset. The reward model, the AI judge we just trained, then judges the generated response and provides a score, the reward signal. The RL algorithm uses this reward score to update the language model's weights. It reinforces the patterns and parameters that lead to high reward, human-preferred outputs, and penalizes those that lead to low reward outputs. It learns through trial and error, guided by the reward model. The outcome of this whole RLHF process is the aligned model, like the ChatGPT you're familiar with today.
Yeah.
This model is significantly better at refusing inappropriate or harmful requests, admitting when it doesn't know something instead of just making stuff up, and providing nuanced, helpful, and seemingly thoughtful responses compared to the base or even the SFT models. This is precisely why your ChatGPT experience feels different, more constrained, more helpful, maybe sometimes a bit more verbose than interacting with a raw GPT-3 model would. It's been carefully sculpted and aligned by this human feedback process, not just raw statistical prediction.
Indeed. It's a powerful technique for alignment. However, it's important to remember this alignment isn't perfect, far from it. The model is optimized to please the preferences of the specific group of human rankers who trained the reward model. This can lead to a specific, sometimes overly verbose or cautious persona as an AI language model. It picks up the style the rankers preferred. It can also, inadvertently, institutionalize any shared preferences or even biases held by that human feedback team, subtly shaping the AI's perspective in ways we might not immediately perceive or agree with. The alignment reflects the aligners.
Okay, so now that we have a sense of how these models are built and trained, let's look at how GPT models are actually being used out there in the real world. Because their transformative impact is becoming evident across nearly every sector of the economy. It's really quite staggering. From how we write software to how businesses engage with customers, it's truly reshaping the landscape. One of the most immediately and profoundly impacted domains has got to be the technology sector, specifically code generation and software development. GPT models, trained on vast repositories of open source code like GitHub, are becoming indispensable tools for programmers. They function almost like sophisticated pair programmers or highly capable coding assistants. Developers can use natural language prompts, just describe what they want in English, get the model to generate corresponding code snippets in multiple languages, Python, JavaScript, SQL, you name it. This significantly accelerates prototyping and development workflows.
Yeah, it's not just generation either. They're also incredibly powerful for debugging and refactoring. They can identify potential bugs in code, explain complex error messages in plain language, suggest fixes, or even rewrite existing code to make it more readable, more efficient, or conform to specific style guides.
Absolutely. And furthermore, they can automate some of the more tedious but critical aspects of software development. Things like generating unit tests and test cases to ensure code quality, or creating comprehensive documentation for APIs and functions, which, as any developer knows, is often neglected but crucial for long-term maintainability. So yeah, if you're a developer listening to this, these tools are likely no longer just a novelty. They're rapidly becoming an indispensable part of the modern toolkit.
And it's more than just a convenience for individual developers, right? If we zoom out a bit, connect this to the bigger picture. GPT isn't just about chat or code snippets. It's fundamentally reshaping how businesses operate across the board. It's turning these vast oceans of unstructured data that companies have emails, reports, customer feedback into actionable intelligence. And it's automating knowledge work tasks that used to consume countless hours of human effort.
Totally agree. In the business and enterprise sector, GPT is driving significant gains in productivity and operational efficiency by automating knowledge work, extracting insights from data, and enhancing customer interactions. We're seeing it used for intelligent customer support, for example. GPT powers these next-gen chatbots that can understand complex conversational queries, maintain context over an entire dialogue, unlike older chatbots, and provide 247 human-like support.
And for data analysis and reporting, too, GPT's ability to process and synthesize vast amounts of unstructured time data from things like customer reviews, survey responses, social media comments, that's invaluable. It can quickly identify trends, analyze sentiment, pinpoint key issues customers are talking about. This transforms raw text into actionable business intelligence in a fraction of the time it would take humans to read through it all.
And then there's workflow automation. GPT is being integrated deeply into enterprise software ERPs, CRMs, SaaS platforms, helping draft emails, summarize long reports or meetings, generate first drafts of legal documents, even create initial versions of HR policies. Products like ChatGPT Enterprise, for instance, offer enhanced security features, data privacy controls, and API access specifically to facilitate these deep integrations within large companies safely. GPT is also being explored quite actively as a transformative tool in sectors that rely heavily on specialized knowledge and personalized interaction. Thinking here about education and healthcare. In education, it can function as a personalized virtual tutor, explaining complex concepts in different ways, providing step-by-step problem-solving assistance, adapting its teaching style to a student's individual pace.
And for educators, it can really streamline preparation time, generating drafts of lesson plans, quiz questions, worksheets, even grading rubrics. For students, it can serve as a powerful research assistant, summarizing dense academic papers, helping brainstorm essay topics, or suggesting ways to structure arguments.
True, but this also raises important questions, doesn't it? Concerns about over-reliance. Could it potentially hinder the development of critical thinking skills or independent research abilities if students just default to the AI? There are studies emerging now. Some suggest that while it might boost participation in things like online discussions, it can also, paradoxically, reduce deeper cognitive engagement with the material itself. A tricky balance.
Definitely a balance to strike there. And similar potential and challenges exist in healthcare. GPT models could potentially act as diagnostic aids for physicians processing symptoms, lab results, patient history to suggest possible differential diagnoses, though this is still very much in the research phase for safety reasons. More immediately, it can automate many administrative tasks that burden doctors and nurses. Things like transcribing doctor-patient conversations automatically, summarizing clinical notes, drafting patient communications. This frees up valuable time for direct patient care.
And for patient education, too. It can translate complex medical jargon into plain language people can actually understand, generate personalized discharge instructions, answer common questions about conditions or treatments in an accessible way. Imagine your doctor spending more time with you and less time clicking boxes on a computer because AI handles some of the admin. That's the promise. Or having a personalized tutor always ready to help you understand a difficult subject in school. Huge potential in both areas. And finally, let's look at the creator economy. GPT has become an incredibly powerful creative and productive force here as well. For content generation at scale, it's being used widely now to write first drafts of blog posts, articles, newsletters, website copy, product descriptions, even video and podcast scripts, or creative outputs like stories and poetry.
It's also an inexhaustible ideation and brainstorming partner, generating lists of blog ideas, catchy headlines, social media content calendars, different marketing angles, all in minutes. And for personalized marketing, by analyzing customer data, GPT can craft highly tailored email campaigns, targeted social media ads, dynamic website content that adapts to the visitor. For example, quickly generating dozens of slightly different ad copy variations optimized for different demographics or customer segments. A/B testing on steroids.
So, okay, pulling this all together, what does this widespread adoption mean for us, for society? Well, GPT is undoubtedly boosting productivity and augmenting human capabilities across the board. This deep dive also makes us ask, are we, as individuals and as a society, potentially sacrificing some of our own critical thinking skills, our creativity, our deeper engagement in the process? This widespread integration of these incredibly capable tools creates this profound societal tension, doesn't it? Between augmenting human capabilities and potentially automating human roles, impacting the future of work and the value we place on certain human skills, it's a big question we're grappling with in real time. Now, while OpenAI's GPT series definitely captured the world's attention and established a kind of early market leadership, it's really far from the only player in the generative AI space, not by a long shot. We're seeing this truly vibrant and intensely competitive ecosystem emerge, with major technology corporations and well-funded startups all developing their own powerful large language models. And importantly, each often has distinct strategies, strengths, and underlying philosophies about AI development. First, let's talk about Google's counterparts, from BERT to Gemini. You have to remember, Google actually invented the foundational transformer architecture back in 2017, so they've always been a central player in AI research. Their earlier models, like BERT, made huge contributions years ago. Their main family of current models is Gemini, which, like GPT-4o, is natively multimodal, designed to understand and process information seamlessly across text, code, images, audio, and even video.
Right, and Google's key competitive advantage really lies in its ability to integrate these models deeply into its vast existing ecosystem. That's their superpower. Think about powering new features in Google Search, enhancing Google Workspace applications like Docs and Gmail with AI capabilities, and providing advanced AI services within the Google Cloud platform for businesses. Their strategy often seems focused on enhancing their existing, widely used products, not just offering a standalone chatbot like ChatGPT initially was.
So they also have strengths in, well, unparalleled data access from search and other services, plus their world-class research division, Google DeepMind. And their models like Gemini 1.5 Pro boast enormous context windows, up to 1 million tokens currently, which surpasses many competitors and makes them ideal for processing massive documents or code bases.
That said, Google's initial product launches for Gemini were sometimes perceived by the market as a bit rushed or perhaps less polished than OpenAI's offerings. It highlights the unique challenges, maybe, of pivoting a massive corporation to compete head-to-head with more agile startups in such a rapidly evolving field.
Okay, then we have a completely different approach from another tech giant.
Yeah.
Let's talk about Meta's open source gambit, the Llama series.
Ah, yes, Meta. What's truly fascinating here is Meta's radically different approach compared to OpenAI or Google. By open sourcing Llama, they're not just creating a product, they're actively trying to build an entire ecosystem around it. They seem to be betting that decentralized, community-driven innovation will ultimately outcompete closed, proprietary systems, at least in many areas. It's a bold strategy.
It really is. Meta, formerly Facebook, has adopted this fundamentally different and highly disruptive strategy. They released their powerful Llama, large language model, Meta AI models under permissive open source licenses. Their core philosophy seems to be about democratizing access to powerful AI tools. They want to foster a global community of developers and researchers who can build upon, inspect, customize, and improve the models collaboratively. They argue this open approach accelerates innovation, allows for greater transparency and public scrutiny, which they believe can lead to safer and more robust systems in the long run.
And the primary advantage of the Llama series is definitely its accessibility and customizability. Developers can literally download the model weights, run them on their own hardware or private clouds, if they have the resources, and fine-tune them extensively for specific tasks or data sets. This offers a level of control and data privacy that proprietary closed models simply cannot match. You own the whole process. This makes Llama a preferred choice for academic researchers who need to inspect model internals and for businesses building highly specialized applications or those with strict data residency requirements.
Now, while the frontier llama models are highly competitive, they generally still lag slightly behind the absolute top-tier proprietary models like GPT-4o or Claude 3.5 Sonnet in overall zero-shot performance on broad benchmarks. And of course, the open-source nature, while empowering for legitimate uses, also means a lower barrier for malicious actors to potentially create and deploy unregulated or harmful versions of these powerful models. That's the flip side. Okay, next up is Anthropic's safety-first approach, the Claude models. This is another really interesting player with a distinct philosophy.
Very distinct. Anthropic was founded in 2021 by former senior members of OpenAI, including Dario Amodei, who left OpenAI reportedly due to concerns about the commercial direction and safety practices there. So, Anthropic's core mission, right from the start, has been centered explicitly on AI safety research and building AI systems that are beneficial and controllable.
Right. Their family of models is named Claude, and they are designed and trained with an explicit focus on creating AI that is helpful, harmless, and honest, the HH criteria. Their key innovation here is a training methodology they call constitutional AI. This aims to align the model not just with human preferences, like RLHF, but with a set of explicit ethical principles or a constitution derived from sources like the UN Declaration of Human Rights or other ethical guidelines. The goal is to make the alignment process more transparent, more scalable, and less reliant on the potentially inconsistent or biased judgments of individual human labelers.
And Claude models have gained a strong reputation for their performance, particularly on tasks requiring creativity, nuanced writing, long-form content generation, and the processing of very long documents. Their latest model, Claude 3.5 Sonnet, offers a remarkable 200,000 token context window, which is huge for analyzing large reports or books. Users often perceive Claude as more thoughtful, more collaborative in its tone, and perhaps more reliably cautious, more likely to refuse potentially harmful or borderline requests compared to some other models. In benchmark comparisons, the top-tier Claude models are highly competitive with GPT-4 and GPT-4o, sometimes even outperforming them in specific areas like coding proficiency or graduate-level reasoning.
On the downside, they typically have a slightly smaller feature set compared to ChatGPT, for example, lacking native image generation capabilities currently. And as a smaller company than Google or OpenAI, their API access can sometimes be more expensive for certain high-volume use cases. And beyond these major players, OpenAI, Google, Meta, Anthropic, we have this broader ecosystem and increasing specialization that adds even more dynamism to the field.
Absolutely. It's not just those four. You have XAI, Elon Musk's venture, with its model Grok, which notably leverages real-time data access from the social media platform X, formerly Twitter, for more up-to-the-minute information. There's Mistral AI, a European company based in France that has gained significant traction very quickly. They're known for producing highly efficient and surprisingly powerful open-source models that often rival much larger competitors, but with smaller resource demands, making them easier to run. You also have companies like Cohere, which focuses specifically on enterprise applications, offering models and tools optimized for business use cases like retrieval augmented generation, RAG, and integrating AI into existing business workflows.
And of course, we can't forget the vast open source community, often centered around platforms like Hugging Face. There's just this continuous release and refinement of a wide variety of diverse models, trained for specific tasks, languages, or data types, pushing innovation from the ground up. So it's really clear that this isn't shaping up to be a winner-take-all game, is it? You, the listener, are likely going to see different models dominating different niches, offering distinct advantages depending on what you need them for, whether it's general-purpose chat, coding assistance, creative writing, data analysis, or running models privately on your own systems. The competitive dynamics are fascinating. It's not just about which model is incrementally smarter on a given benchmark, but also about this fundamental philosophical divide between proprietary, closed systems and the burgeoning open source ecosystem. It's a hugely dynamic and exciting space to watch unfold right now. #7, Challenges and Ethical Frontiers. Okay, so as these GPT models become more powerful and more deeply integrated into our daily lives and work, it's absolutely crucial that we also confront the significant limitations, the inherent risks, and the complex ethical dilemmas they present. And these aren't just minor bugs that can be easily patched. Often, they're deeply rooted in the current paradigm of how these models are designed and trained. One of the most well-known and persistent flaws is the problem of hallucinations, or maybe more accurately, confabulation, and the related issue of misinformation. This describes instances where the model generates content that is nonsensical, factually incorrect, or entirely fabricated. It presents it with this air of confidence and authority, making it seem plausible.
Yeah, and what's truly insightful, or maybe worrying here, is that hallucinations aren't really a bug in the traditional software sense. They're almost an inherent feature or side effect of how these models are fundamentally designed to work. Remember, their core objective is to generate the next statistically plausible token, not necessarily the truthful or factually correct token. That distinction is critical. Hallucinations are an emergent property of that core objective. LLMs don't possess a true understanding of the world. They don't have a built-in database of verified facts or the ability to reason rigorously about truthfulness like humans ideally do. Their knowledge is essentially a vast, complex statistical representation of the patterns they observed in their training data. So when faced with a prompt for which they have insufficient or conflicting data in their training, or when asked about events that occurred after their training data cutoff date, their core function compels them to generate a statistically likely sequence of words anyway, even if it has absolutely no basis in reality. They fill in the blanks plausibly. And this can be exacerbated by ambiguous prompts from the user or the model's inherent tendency to try and maintain fluency and coherence at all costs, even if it means making things up.
And the consequences of these hallucinations can range from just benignly amusing and low-stakes creative tasks to dangerously misleading in high-stakes domains. We've seen real-world examples, lawyers facing court sanctions for submitting legal briefs containing completely hallucinated case citations generated by ChatGPT. That actually happened. In medicine, a model could potentially generate incorrect diagnostic information or harmful treatment advice if not used very carefully under expert supervision. And perhaps most broadly, the ability of LLMs to generate vast quantities of plausible-sounding but false content at scale poses a significant threat of large-scale misinformation campaigns. This could erode public trust in institutions and pollute the online information ecosystem even further than it already is. This is why always verify has become the golden rule when using AI for any kind of important factual information. You just can't take its output at face value. Another critical challenge we need to unpack is algorithmic bias. As we discussed, these models are trained on vast swaths of the internet and digitized books. These sources are repositories of human culture, human knowledge, and inevitably deeply ingrained human biases and stereotypes. Consequently, even a perfectly functioning model, just by learning the patterns in that data, will learn, reflect, and often even amplify these societal biases.
Yeah, this is a really complex and pervasive issue. The primary source of bias is often the training data itself, as you said. If the data contains stereotypical associations, for example, consistently associating certain professions primarily with specific genders or certain negative characteristics with specific racial groups, the model will learn these statistical correlations and reproduce them in its outputs. This can then be compounded by algorithmic design choices made during model development that might inadvertently favor certain outcomes over others. For example, a UNESCO study found that several popular LLMs often assign more diverse, high-status jobs like engineer or doctor predominantly to men when prompted, while frequently relegating women to roles like homemaker, domestic servant, or even prostitute based on learned associations in the data. There's also something called position bias, where models tend to give more weight or attention to information presented at the very beginning or very end of a long context window, potentially ignoring critical nuances or counter-arguments buried in the middle.
And the real-world consequences of these biases can be significant and harmful, leading to discriminatory outcomes in areas like automated resume screening, loan applications, or even potentially influencing clinical diagnoses. Studies have shown, for instance, that GPT-4 can sometimes perpetuate harmful race and gender stereotypes in its diagnostic suggestions if not carefully prompted and reviewed by a human expert.
And mitigating these biases is incredibly challenging. Simply trying to filter the training data is often insufficient and can be like playing whack-a-mole. Plus, as we mentioned earlier, even the human labelers involved in the alignment process, SFT and RLHF, can inadvertently introduce their own preferences and biases into the model, potentially leading to new forms of subtle bias.
So yeah, what this means for fairness and equity is stark. If the internet reflects societal biases, then the AI trained on it will inevitably inherit those biases. And sometimes, due to the scale and amplification effects, it can make those biases even more potent or pervasive. It's almost like holding up a massive high-fidelity mirror to our own societal imperfections, but one that can then act on those imperfections at scale.
And thinking about scale, this raises another important question. As these incredibly powerful models become more ubiquitous, what's the true cost to our planet? The incredible capabilities of AI come with a very real and tangible environmental footprint that we simply can't ignore. It's not free magic.
That's a crucial point, often overlooked in the excitement. Let's talk about the environmental footprint, specifically energy and water consumption. The immense scale of developing and running these frontier LLMs comes at a significant environmental cost. These processes are incredibly resource-intensive. Training a model like GPT-4 requires millions of hours of computation running on thousands of high-powered GPUs, usually housed in massive, energy-hungry data centers. This consumes a staggering amount of electricity, contributing significantly to carbon dioxide emissions, especially if those data centers are powered primarily by fossil fuels.
To give you a sense of scale, one 2021 study estimated that training just a single large language model, a predecessor to GPT-4, consumed enough electricity and generated enough CO2 to be equivalent to the entire lifetime emissions of several gasoline-powered cars, just for one training run. And the environmental impact doesn't stop with training. The inference stage, that's when users like you and me actually interact with the model, sending queries and getting responses, is also surprisingly energy-intensive. A single ChatGPT query is estimated to consume multiple times more electricity than a simple Google search query. It adds up quickly with millions of users.
Furthermore, these data centers require vast quantities of fresh water, primarily for cooling their densely packed hardware to prevent overheating. It's been estimated that the training of GPT-3 alone consumed approximately 700,000 liters of fresh water. Think about a small swimming pool's worth. And ongoing inference also requires significant water, with one estimate suggesting around half a liter, like a standard water bottle, for every 20 to 50 user requests processed by the model. This can place considerable strain on local water supplies, particularly for data centers located in already water-stressed or arid regions. It's a sobering thought that every query you make has this tiny but real and cumulative environmental impact. And finally, we absolutely must consider the critical issues around privacy, security, and the future of data in the age of GPT. The use of web-scale data for training, combined with user interactions potentially being used for further refinement, raises critical privacy questions. LLMs have been shown, in some cases, to memorize and inadvertently regurgitate snippets of their training data, which could include sensitive personal information like names, email addresses, phone numbers, or private details if that information was present in the original scraped data. This poses a significant privacy risk.
And for enterprise users, there's a major concern, quite rightly, that proprietary or confidential business data submitted to a public-facing model could potentially be used for future training or inadvertently leak, compromising trade secrets or sensitive customer information. This has, of course, led directly to the development of enterprise-grade versions of these models, like ChatGPT Enterprise or Google Cloud's offerings, that come with much stricter data privacy controls, contractual guarantees, and often run in isolated environments.
In terms of security vulnerabilities, LLMs are susceptible to various forms of adversarial attacks. One well-known example is prompt injection, where a malicious user crafts a clever prompt designed to trick the model into bypassing its safety filters or alignment training. This can lead it to generate harmful, biased, or inappropriate content that it's normally supposed to refuse. It's a constant cat-and-mouse game between attackers and defenders.
And as these models gain more agency, the ability to interact with external tools, browse the web, send emails, execute code, the risks associated with such vulnerabilities increase dramatically. An exploited agent could potentially do real damage.
Then there's the whole thorny issue of copyright and intellectual property. This is huge right now. The legality of training LLMs on vast amounts of copyrighted material, like books, articles, images, code, without explicit permission from the creators, is the subject of intense debate and numerous high-profile lawsuits currently underway. It raises fundamental questions about the doctrine of fair use in the context of AI training data, and related questions about the ownership of the model's output, who owns the text or image generated by the AI. Can AI-generated content even be copyrighted under current law? These are massive legal and economic questions being hashed out right now. This deep dive really shows us that as AI gets smarter and more capable, the questions around who owns the data, who's responsible for the AI's output, especially when it's wrong or harmful, and how we protect our privacy and security become incredibly complex and increasingly urgent. So after exploring the origins, the architecture, the training, the applications, and the challenges, where's all this headed? What's next for GPT? The trajectory of generative pre-trained transformers is accelerating at just an incredible pace. It feels like it changes month by month. We're pushing beyond just next word prediction toward more sophisticated forms of artificial intelligence. OpenAI's public roadmap, coupled with broader trends we're seeing across the entire field, points to a future focused on unified intelligence, more advanced reasoning capabilities, and increasingly autonomous AI agents, all explicitly framed by many, including OpenAI, as part of the long-term quest for artificial general intelligence, or AGI. OpenAI specifically has signaled a pretty clear strategic direction for its roadmap going forward. They seem to be moving away from having this sometimes confusing menu of slightly different models, like GPT-4, GPT-4 Turbo, etc., towards eventually offering a single, unified, and much more intelligent system. The path to their next major version, presumably GPT-5, includes several anticipated interim releases. GPT 4.5 has been previewed, possibly for early 2025, and is presented as a model with a broader knowledge base, and improved ability to understand and follow user intent, and maybe even greater EQ or emotional intelligence, aiming to make interactions feel more natural and intuitive.
Right, and this is expected to be followed by announced plans for GPT 4.1 and potentially other iterations. These are rumored to bring major gains in specific areas like coding proficiency, better instruction following, and potentially massive context windows, maybe up to 1 million tokens or more, catching up with competitors like Google Gemini.
Exactly, and the vision for GPT-5 itself, according to comments from CEO Sam Altman, is probably not going to be a single monolithic model, but rather an integrated system that unifies multiple underlying OpenAI technologies. Things like the advanced reasoning models they're developing in their O series, the multimodal capabilities from GPT-4o, voice, vision, and integrated tools like web search and code execution, all accessible, hopefully, under a single intuitive interface.
Yeah, a key goal seems to be eliminating the need for the user to consciously choose a specific model or mode. Should I use the data analysis mode or the web browsing mode? Instead, creating an AI that can intelligently determine on its own when to give a quick factual answer versus when it needs to engage in deeper, more computationally intensive thought or use specific tools to solve a complex problem. More autonomous decision-making by the AI itself.
Imagine your AI assistant just knowing when to quickly answer a fact versus when it needs to spend, say, 30 seconds really thinking through a complex reasoning problem for you. That's the kind of adaptive intelligence they seem to be aiming for. And a crucial part of this roadmap also appears to be democratizing access further. OpenAI has needed a plan to make a standard intelligence version of GPT-5 available for free to all users, with paid subscribers gaining access to higher tiers, with more compute, faster responses, and more advanced capabilities. This strategy would likely accelerate its broad societal integration even faster than ChatGPT already has. Now, beyond OpenAI's specific roadmap, the entire field of AI research is intensely focused on these key research frontiers that move beyond simple next-word prediction. The aim is really to imbue these models with capabilities that are more analogous to human cognition. One primary challenge, as we've touched upon, for current LLMs is their relative weakness in advanced reasoning, multi-step, logical, causal reasoning. While they can often recognize patterns associated with reasoning from their training data, they don't typically reason in a truly robust, verifiable step-by-step way like humans can. So research focuses intensely on eliciting and improving this. Through clever prompting techniques like chain of thought, K-ready prompting, where the model is explicitly instructed to think step by step or show it's working, this has been shown to significantly improve performance on complex reasoning tasks.
And companies are also developing specialized models explicitly for reasoning, like OpenAI's internal O-series models, O1, O3 were mentioned in relation to GPT-4's development, or models from other labs like DeepSeek R1. These are specifically designed to excel at complex logic, mathematics, and science problems, perhaps by internally evaluating multiple potential reasoning paths or employing different computational strategies.
Another huge frontier is agentic systems. This feels like the next major evolutionary step for LLMs, transforming them from basically passive tools that respond to prompts into proactive AI agents that can autonomously pursue complex multi-step goals on behalf of a user. This requires a whole new set of capabilities beyond just language generation, things like planning, the ability to break down a high-level goal like plan my trip to Italy into a sequence of executable steps, tool use, allowing the agent to interact reliably with external software and APIs, things like web browsers, email clients, booking systems, calculators, or code interpreters, and robust memory, the ability to maintain context, store information, and recall relevant details over long interactions or complex tasks.
Right. OpenAI's own demonstration of a ChatGPT agent, which seemed to combine web browsing, research synthesis, data analysis, and code execution into a single task, is an early, powerful example of this trend towards agentic AI.
This is where it gets really compelling and maybe a bit science fiction-y. The goal isn't just smarter answers anymore, but an AI that can potentially plan, execute tasks, use tools effectively, and interact with the digital world almost like a competent digital colleague or assistant. That's a massive leap beyond just generating plausible text. And then there's the ongoing push towards true multimodality. While models like GPT-4o can already process multiple data types, text, image, audio, the ultimate goal is to create systems that can understand, reason across, and generate content in any combination of modalities, text, image, audio, video, maybe even other sensor data seamlessly and fluidly.
Yeah, this would allow for a much richer and more holistic understanding and interaction with the world, much closer to how humans perceive reality through multiple senses simultaneously. Imagine generating a complete, edited video from just a simple text script, or having a continuous spoken conversation with an AI about a live video feed from a drone or a security camera, allowing the AI to truly see and hear and comment on its environment in real time. Groundbreaking applications there. And this relentless progress, particularly towards reasoning and agency, inevitably brings us back to that ultimate, profound question about the very nature of intelligence itself. Is artificial general intelligence, AGI, simply a matter of scaling up current architectures like the Transformer with ever more data and compute power? Will intelligence just emerge? Or are there fundamental qualitative leaps still required? Are there missing ingredients in our current approaches that we haven't even conceived of yet?
And that's exactly it. All of this rapid progress brings us squarely to GPT's role on the path to artificial general intelligence, or AGI. The surprising emergent capability give unexpected tasks, their performance on complex human-level exams, their demonstration of nascent theory of mind capabilities, led some researchers, including a prominent team from Microsoft, to publish papers arguing that GPT-4 demonstrated sparks of AGI. A controversial claim, but it sparked debate. This has really fueled a central debate within the AI community. On one side, you have the scaling hypothesis. This posits that AGI might actually be achievable simply by continuing to scale up current transformer-based models, more data, more compute, more parameters. The belief is that the emerging capabilities we've seen so far will continue to appear and strengthen with scale, eventually leading to general intelligence.
But on the other side, you have the missing components argument. This perspective holds that current architectures, like the Transformer, have fundamental limitations, even at massive scale. Proponents argue that true AGI will require fundamentally new breakthroughs, entirely new architectures or paradigms to achieve capabilities that current models lack. Things like robust causal reasoning, understanding true cause and effect, not just statistical correlation, reliable long-term planning and memory. Embodied learning, the ability to learn directly from interaction with the physical world, not just text data. And maybe even true understanding or consciousness, beyond just sophisticated statistical pattern matching. What does it even mean to understand?
This really is the big philosophical and scientific question hanging over the entire field of AI research right now. Can we build true general intelligence simply by scaling up what we have now? Or are we just creating incredibly sophisticated mimics, lacking some essential spark? The most likely path forward towards AGI, many believe, will probably involve a convergence of these approaches. Continued aggressive scaling of powerful foundation models like GPT, yes, but likely combined with new architectures, new training techniques, and new approaches specifically designed to integrate robust reasoning, planning, causality, and perhaps even cognitive structures that more closely mimic the flexibility and efficiency of human thought. Hashtag tag tag outro. Wow. Well, we've certainly covered a lot of ground today. We've journeyed through the incredible origins of GPT, broken down the architectural genius of the Transformer and self-attention, traced its breathtaking evolution from the relatively modest GPT-1 all the way to the omnimodal capabilities of GPT-4o, and explored how it's fundamentally reshaping everything from software development to education to the creative industries. We've also grappled with the very real shadows that cast, the persistent problem of hallucinations, the challenge of inherent biases, the significant environmental cost, and the complex issues around privacy and security.
Absolutely. This deep dive, I think, truly underscores that GPT isn't just another piece of technology. It's a profound force actively reshaping our world as we speak. Understanding its underlying mechanics, its remarkable strengths, and perhaps most importantly, its crucial limitations and potential pitfalls, is no longer optional knowledge for tech enthusiasts. It's becoming essential literacy for every one of us trying to navigate this rapidly changing landscape.
So as these models continue their relentless evolution, becoming ever more intelligent, more agentic, as we discussed, and inching closer perhaps to that still elusive idea of AGI. Here's a final thought for you, our listener, to ponder as you go about your day. How do you think the balance of responsibility should shift between the creators of these incredibly powerful AIs like OpenAI, Google, Anthropic, and the users, the individuals and organizations who deploy them out in the world? What role should we, as individuals and as a society, play in actively shaping a future where AI truly benefits all of humanity without compromising our core values or exacerbating existing inequalities? It's a conversation we all need to be part of.
Indeed. That's the critical question. The journey of GPT and AI is far from over, and its ultimate destination, its ultimate impact, will be determined not just by the next technological breakthroughs, but crucially, by the ethical frameworks we establish, the regulations we implement, and the societal choices we collectively make along the way. Your critical thinking, your engagement with these issues, is more important now than ever before in this unfolding story.
Thank you so much for joining us on this deep dive into the world of GPT. We hope you found it insightful. Until next time, keep questioning, keep learning, and keep diving deep.